So because that hydroxyl group is an ortho para director, I decided to draw the ortho derivative next. This is not a chloro group, though. This is an isopropyl group. And it could either be 2 isopropyl phenol or ortho isopropyl phenol. And for the final example, the other position that's possible for the substituent on this ring is the third carbon, right? And on the third carbon, we find a nitro group. And so, now incidentally, we can name this right now, but we can also review a little bit this ortho, para, or meta director situation we got going on here. So 3-nitro phenol or meta nitro phenol. Let's talk a little bit though about making this thing. What if you wanted to make meta nitro phenol? Well, if you wanted to start with benzene, for example, what group do you think that you should put on the ring first? And what you want to think about is, okay, I know that the hydroxyl group is an activating substituent, right? It's feeding electron density into the ring. And if the ring in electrophilic aromatic substitution is going to be the nucleophile, wouldn't it be nice to shower it with some electrons? So the hydroxyl group being the activating species, we went through all the resonance forms. We know that it is an ortho-para director. The nitro group is a pretty decent electron withdrawing group, right? So it deactivates the ring. It sucks electron density out of the ring, making it a poorer nucleophile, but it's also a meta director. And we went through drawing those resonance forms. We discussed the directing ability of these substituents. So if I want these guys to be in this meta relationship, right, this 1-3 relationship on the ring, wouldn't it stand to reason that I would put the group that is the meta director onto the ring first? Yes, that is common sense, right? So you would put the nitro group onto the ring first, and then you would add the hydroxyl group, probably cook that thing up with some sodium hydroxide, right? Molten sodium hydroxide, and add the hydroxyl group to the ring, and it would be directed in the meta position because the nitro group would already be there, right? If you put the hydroxyl group on first, then you would direct that nitro group to the ortho-para position. So one thing we didn't talk about in the aromatic chapter was the nucleophilic aromatic substitution. Getting that hydroxyl group onto the ring can be a little tricky. There's a few different ways you can do it. You can take benzene, right, and subject it to a nitration reaction, right, where you'd stick the nitro group on there, and now the next thing you're going to want to do is you're going to want to add the hydroxyl group in the meta position. Well, the nitro group is a meta director, so that's fine. But if you want a nucleophile to attack the ring and not have the ring attack, right, as in electrophilic aromatic substitution, then possibly you might want to put a good leaving group on the ring where you want the hydroxyl group to be, and then say use sodium hydroxide, the hydroxide anion, as a nucleophile and displace some other leaving group. We did not, your book doesn't really go into nucleophilic aromatic substitution, but if you put a sulfonic acid in that position, that's not a bad little leaving group. It's better than the nitro group, right? You have to think back, like what makes a good leaving group? Okay, well, the weaker the base, the better the leaving group. So I'll let you guys look up the pKa of those two different leaving groups and just keep that sort of in your back pocket. When you're trying to design a synthesis, you want to think about these things, like what group do I put on first? You know, if I want this relationship on the ring, et cetera, et cetera. So speaking of reactions, let's go through a few that we can do with alcohols. And the first one is going to be sort of reminiscent of something that we talked about in the previous chapter, right? We can do an elimination reaction, but specific to alcohols, we can do what's called a dehydration reaction. Dehydration, so that sort of speaks for itself, right? We're going to remove water, but so how are we going to do that? So let's just pick a nice, easy, kind of short molecule to deal with here. Let's choose... all right, let's just pick this molecule. So we're going to start out with the alcohol. So you can use why don't we pick isopropanol, since that's what we've been using. If I were to protonate this, and I could just put H+, but let's be specific. Your book uses sulfuric acid and some heat. And what you're going to get out the other side is, whoa, how did that happen? An alkene, right? So here I have an alcohol, and over here I have an alkene. So what's going on? All right, I got to tell you, we just talked about the leaving ability of the leaving group, right? And we talked about how leaving groups aren't especially awesome if they are kind of strong bases, right? So the weaker the base, the better the leaving ability of the leaving group. So do you think that hydroxide is going to be a good leaving group? And so if you're staring at the acid over the reaction arrows, you already know the answer is no. And so what you're going to do then is you're going to use the lone pairs of electrons on the oxygen, right, to deprotonate the acid. So basically we're going to protonate the alcohol. So let's draw this out. So here is isopropanol. And what we're going to do is, and I'm just going to draw H+. H2SO4 is a source of a proton, right? We don't have to draw that whole molecule out. We're going to grab that proton and we're going to protonate our alcohol. So OH2+. Now, what do you think is a better leaving group, H2O or OH-? Well, water is a weaker base than hydroxide, right? And so water is going to be a better leaving group than hydroxide. So we have protonated the alcohol, now creating ourselves a better leaving group. So this is just going to split, take the electrons with it, and what you get is, in this case, a secondary carbocation. Let me draw this just a little bit more suggestively here, because I've got some water floating around in here, and you can use it as a base to take the hydrogen off of the carbon that's next to the carbocation. And we get an alkene. And we'll probably reprotonate the conjugate base of the sulfuric acid, whatever. So you get your alkene. This is an elimination reaction, right? What kind of an elimination reaction is this? What happened here? Well, first we created a decent leaving group, and then it took off. And when it took off, we were left with a carbocation. Then the beta carbon was deprotonated, and the electrons collapse between the two carbons, and we end up with a double bond. This is an E1 reaction, right? Your leaving group left, and then you create the carbocation. If this was an E2 reaction, this would have been one fell swoop, right? So this would have been a bimolecular situation. If this was E2, where you would have deprotonated the beta carbon, the electrons would have formed the double bond, and the water would have taken off all in one fell swoop. But the water took off first, leaving the carbocation, and then we took the hydrogen off of the beta carbon, and we formed the alkene. So this is an E1 reaction. And it's a specific type of E1 reaction. It's called a dehydration reaction. So this is an E1 reaction that we can do to dehydrate an alcohol and make an alkene. So just like when we talked about in the last chapter, the order of reactivity for dehydrating alcohols is going to sort of speak to the stability of the carbocation, right? And we know that these carbocations are stabilized through hyperconjugation with those p electrons that only a good substituent can give you, right? You know, in other words, not a hydrogen. So we get a tertiary carbocation, which is going to be more reactive than a secondary carbocation. So if I take one of those R groups away, I have a secondary carbocation, and then a primary carbocation is not going to be very stable at all, right? Because what are we doing? We're taking away the ability to stabilize that positive charge through hyperconjugation. Hydrogen doesn't have any p electrons, folks, so we're not nearly as stable with a primary carbocation as we are with a secondary, as we are with a tertiary. So the order of reactivity for dehydrating an alcohol is going to be primary, then secondary, then tertiary. Tertiary being the most reactive. So we can write that down here. So most reactive and least reactive.